Good evening, students. Hope you are all doing well. Again, this is the sixth day of our theoretical class, which include the second paper, MCH-002 paper, and in the last 5 days we covered block 1, 2, 3, 4, and only the high performance liquid chromatography. Some part was remained, which we will cover in the in our latter part. Today we will move to block 5, that include your two units, unit 11 and unit 12. Unit 11 is all about your membrane separation, that is by using some barriers. We will separate the mixture or separate the components in a mixture by a different mechanism and techniques, and depending upon the pore size of the membrane or the barrier, different types of membrane separations are there. We will discuss in details in this unit, unit 11, and in unit 12, that is the last unit of your paper MCH-002, and that include your electrophoresis. So unit 12 is all about migration of ions, migration of ions to their respective electrodes. That means positive ion will move to or will migrate to negative end of the electrode, and the positive ion, that is the cation, will move to negative part. And what type of mechanism and what type of electrophoresis techniques are there, we will discuss in the latter part of today's discussion. And already we have discussed up to unit 4, we have discussed many separation technique that includes some physical methods, and mainly we have discussed different type of chromatographic methods. That chromatographic methods are very important from your study as well as your examination point of view. So for today's class, we will start with membrane separation first. So now I am sharing my screen with you. So students, I am clearly audible or any problem? If you have, I think it is okay from my side. Somen Roy sir, it is okay? I am audible?
Yes, sir.
Okay, okay, okay. Please mute. Somen Roy sir, please mute. Okay, thank you. So the basic part of this unit, membrane separation, we will cover by from this PDF, and in the latter part, some technical part, we will have one PDF, PPT. So we will move there. So let's start with the first part, that is the membrane separation. This is just like using a cloth for the filtration of water. So that cloth is treated as the membrane or the barrier, which separates different particles or different impurities from water, and we will get pure water. That is a traditional way of filtration. And under a technical point of view, we have many types of membrane separations are there. That there is reverse osmosis process, which is a vital or an important aspect related to our water purifiers, that is RO. And we have nanofiltrations are there. In this nanofiltration, the pore size is in the nano scale, and in ultrafiltration, the pore size is less than 1 nanoscale. Then we have micro label filtration. Then we have dialysis. Then electrodialysis also there. Gas separation and pre-evaporation. And at the end, we have liquid membrane process. Then under mechanism, we have some separation through membranes like sieving, solution diffusion, and then preferential sorption, capillary flow. Then you have Donan effect, Newton flow, surface flow, etc. These things are there. So at the end, we have the application part. So I just try to cover these long unit within 1 hour. So I will move just a little fast. So hope you will cope up. So this separation technique involved the use of a membrane, or in other words, the use of a barrier to separate the different components of a mixture. So this separation depends on the type of membrane which we are used, and the type of sample which is to be separated. For example, in osmosis, this is a separation technique in which the membrane used is called as semi-permeable membrane. So under semi-permeable membrane, the uniqueness of semi-permeable membrane is it allows the solvent particles to pass through it, leaving the solute particles. That means if I have a solution with solvent and solute particles, then the SPM, that is semi-permeable membrane, will allow the solvent particle, that is the only the water, and the solute particle will remain. So this is the characteristics of our semi-permeable membrane. And there is also perm selective membranes are there, which are readily used for membrane separation. So this the various objectives of this unit are to explain the general aspect and importance of membrane process, understand and explain the various mechanism involved in it, define the term like product flux, solute retention percentage, percent recovery, membrane fouling, and concentration polarization. And also it will explain what is osmosis, reverse osmosis, dialysis, and electrodialysis process. And at the end, we have some important applications based on membrane separation. So the general aspect of membrane separation is all about use of membrane to separate different components of a mixture. So let us have this pictorial form of separation, that this is the membrane which we are used for the separation. This is the membrane which is placed diagonally in this square type vessel, and we have two components A and B. If I put the solution with the two components A and B here, then either A or B with permeate means it will flows through. This is known as permeation, that it allows the um, particles to pass through it. This is known as permeation. So either A or B will permeate, and again the component which is permeate, the second component will left out or will be separated. So this is the general view of your membrane separation process. There are two bulk phases are separated by a barrier which is called membrane. So membrane is nothing but a barrier. The membrane controls the passage of different chemical substances through it, which depends upon the nature of the chemical substance and the membrane. So the separation depends on generally or based on two important factors, that is what type of chemical substance to be separated and what type of membrane we are accordingly used. Then we have some different types of membrane based on their pore size. Then we have non-porous, microporous, mesoporous, or macroporous. So these are things are there. So according to IUPAC, that is International Union for Pure and Applied Chemistry, if the pore size is between 20 angstrom to 500 angstrom, then this membrane is said to be mesoporous. If the pore size is more than 500 angstrom, then it is called macroporous. So non-porous means the membrane will have no pores. So a membrane can also either be solid or a liquid. It can be a polymeric material, inorganic refractory compound, or a metal of their composites. So this is the type of membrane on the basis of size of the pore. Then the permeation, it is another factor which defines the quality of the separation through membrane. That what type of membrane is allowing what type of substances to pass through it. It is known as the permeation. So permeation is generally applied to liquid and gaseous components. If a component is liquid or at gaseous state, then this permeation will effect will be effective. The permeation of chemical species across the membrane is kinetically driven by the application of mechanical, chemical, or thermal work. So the permeation is either by we will say it is driven by the application of mechanical force, chemical bonding, or some thermal work. So these things are there. The performance of membrane is defined in terms of two simple parameters, that is transmembrane flux and solute retention or solute selectivity. So there are two factors which define the performance of a membrane, that is transmembrane flux and solute retention or solute selectivity. So the transmembrane flux or permeation flux, this transmembrane is nothing but your permeation. It is the rate permeation rate is the volumetric or mass or molar flow rate of the fluid passing through unit area of the membrane per unit time. So per unit area of the membrane surface per unit time, how much by volume, by mass, or by molar unit the fluid is passing through it, it is known as the transmembrane flux. That is in unit measurement. Transmembrane flux of any species is directly proportional to, that is in terms of I, that is proportional to the driving force applied across the membrane. What type of force is applied for the permeation, and is inversely proportional to the thickness of the membrane. So when the membrane is more thick, the permeation will be less. That means it's inversely proportional. The For effective separation by membrane or through membrane, the thickness should be less. If it is less thick, then the permeation will be more or fast. If it is more thick, the permeation will be less. If the driving force is described in terms of hydrostatic pressure gradient, that is delta P, the hydrostatic pressure gradient, or partial pressure difference delta Pi, or concentration difference delta Ci across the membrane for any species, then species I, then Ji, that is the transmembrane flux for ith species, it is equal to Pi, it is equal to Pi into either it is delta P, that is hydrostatic pressure gradient, or delta Pi, that is partial pressure gradient, or delta Ci, that is the concentration difference, divided by delta. Delta is the difference. Sorry, delta is the unit area, delta. So where Ji is the transmembrane flux, the permeability of the ith, then the ratio of permeability of I to effective membrane thickness is sometimes called permeance. Just remember this word, permeance. That is The permeability to effective membrane thickness is known as permeance. That is the membrane thickness, how it is related to the ratio of the permeability of species is known as permeance. The retention of selectivity is a measure of relative permeation rate of different components through the membrane, and it is expressed in terms of selectivity coefficient alpha. This is the retention of selectivity, that is measure of the relative permeation rate of different components. So this is selectively measure. So this is known as selectivity coefficient alpha. And the selectivity coefficient alpha, if we have two components A and B, this will be PA by PP. If and this is in terms of pressure, hydrostatic pressure. If in terms of concentration, this will be concentration of A and concentration of B in at constant pressure divided by concentration of A slash concentration of B at constant concentration. So this will be divided. Here P stands for your permeate and C stands for your concentrate. Some important membrane processes are so there are different type of membrane processes for different separation techniques using membrane or barrier type separation. So uh, there are a number of membrane processes which can be defined by considering the following aspects or factors. The aspects that are very much effective for to define a membrane process include separation objective, the nature of the substance which needs to be separated, number one. The nature of the species retained by the membrane, that is the residual part which is retained by the membrane. The nature of the species permeating through the membrane, that is the filtration part which gets filtered or sieved or permeated. The driving force needed to achieve the desired separation, that is what type of force which are applicable. It may be mechanical force, it may be chemical bonding, it may be some thermal effect. So these things are there, and what mechanism is involved in separation. So these are the so these are some important factors or important aspects which on the basis of which different membrane separation techniques are evolved. The first one is reverse osmosis. In reverse osmosis, what happen? Generally, we know that first we will discuss what is osmosis. Then we will move. The opposite effect is known as reverse osmosis. So, what is osmosis? Osmosis is by using a semi-permeable membrane that allows only the solvent particle to pass through it. So, what happen? The in osmosis there is separation of solvent particle. The separation of solvent particles from the solution, and the solute particle remained at the one end, and that is at the residual part, and the solvent particles will remain will be at the filtration part, that is at the opposite end. So in reverse osmosis, what happened? There is movement of solute particles, and the solvent particle remain intact. This is the use of your reverse osmosis process, which is used in generally in the water purifiers. So reverse osmosis is a process where a relatively pure solvent, just remember this, pure solvent means it has less concentration, is separated from a salt solution. Salt solution means this is higher concentration, whereas solute percentage is more. So by using semi-permeable membrane by the application of hydrostatic pressure. So here the pressure of water is there or solvent is there. So this is the pressure is hydrostatic pressure, and here we get pure solvent, that is pure water with low concentration of the solute from salt solution, that is from ordinary water, that is more concentration. So the solvent will flow from more concentration to lower concentration. But in osmosis, what happen? There is a movement from low concentration to higher concentration. So this is just a reverse effect. The hydrostatic pressure is ranges from 2 megapascal to 6 megapascal MPa, and some specifications are written here that effective size is less than 10 angstrom is used in RO. Then this is the schematic representation, that if this is the solution part, that is the ordinary water with higher concentration of the impurity or the solute, and then by using the semi-permeable membrane, what happened? It allows only the solvent particle to pass through it. So here what happened? Only the water, the pure water will flow, and your impurity or the solute will remain intact with this semi-permeable membrane. So the filters we have used in our in water purifiers, these are nothing but containing your semi-permeable membranes. So the next is nanofiltration, where the pore size is in nano scale or very minute. The pore size is your 10 to 30 angstrom, and here the pressure used is 1.5 to 2 MPa. And generally, organic solutes of low molecular weights get separated by this process. This is nanofiltration. What is ultrafiltration? In ultrafiltration, the pore size is 30 angstrom to 200 angstrom. So the pore size becomes larger, that is 30 angstrom to 200 angstrom, and the pressure involved is 500 kPa. So when the pore size varies, the mode of operation will also vary. And for this by this process, the separation of colloidal space particles, oil, macromolecules from effluents, water, as well as from surface water can be done. And then we have microfiltration. For microfiltration, the pore size is submicron size, that is greater than 0.1 micromolar. So the pore size is becomes larger, and here the pressure is 100 kPa or so. So this is in micro level. That is 10 to the minus 3 micro level pore size. And when the size is in micro level, this is microfiltration. And accordingly, water samples, removal of bacteria from water sample, removal of submicron size suspended dust and particulate matters from gas streams. These are some applications of your microfiltration. Then we have dialysis process. As we know, dialysis, it is this process also used in our medical field, that impure blood is uh, impure blood is replaced by pure blood. The process of dialysis is applied there. So in the dialysis process, the pore size is around 20 angstrom to 60 angstrom. And what happened, just to see here, this is one, I have one PPT which include your dialysis. Yes, this one is the dialysis process. Here, for a patient with infected blood is replaced by the pure blood of the same group by using the process of dialysis. So here the some pneumatic pressure is applied, which is known as blood pump, and here the impure blood is separated, removal of the blood, and simultaneously pure blood is injected into the patient body. And these are some medical terms are there. So just you remember that this dialysis process is used in medical field for replacement of impure blood to pure blood. Okay. So dialysis is a membrane process in which a microsolute permeates across a membrane as a result of concentration gradient from a given feed solution to another receiving solution with a common solvent. That means here two ends are there, that is given feed solution to another receiving solution. So there are two ends, one is your feeding and another is your receiving end. That at one end impure blood goes out, and at the other end pure blood is into the patient's body. The common fluid phase from the microsolute are removed is designated as feed phase, whereas the fluid phase which receives the microsolute is designated as dialysate. The most common application of dialysis is the purification of blood to reduce the toxic and end products of metabolism in a patient whose kidney has failed. It is the single largest application of dialysis process and is known as hemodialysis or artificial kidney. The process is discussed in detail in subsequent section of this unit. So this is an important application in medical field in the kidney diseases, that where the kidney failure is seen. This dialysis process, or also known as the hemodialysis, it is mostly applicable or applied to that patient. So in electrodialysis, what happened? In electrolysis, we have used the electrical field, that is from electrical application we will separate the components. In electrodialysis process, electrolytes are removed from one solution to other, and it is used for desalination of saline water. So the desalination will occur by the use of ED. The cation anions were permeate through the cation selective and anion selective membrane respectively as a result of applied electrical energy. So there are two membranes are there, cation selective membrane and anion selective membrane. So by using these two opposite charge selective membranes, and by the application of electrical energy or electrical field, this electrodialysis process is employed for desalination of saline water. Even though reverse osmosis dialysis are both useful for desalination, there is a fundamental difference between two is that in RO, the solvent permeates through membrane and solute, both electrolyte and non-electrolyte are retained, but in ED, the ED permeates through the membrane and the solvent and non-electrolytes generally do not permeate through the membrane. So in RO, what happen? We separate pure solvent from the solute. So the solute, it may contain your electrolyte part and non-electrolyte part. So in RO, whether it is electrolyte or non-electrolyte part, it will separate from the pure solvent. But in electrodialysis, what happen? There is separation of the solvent with electrolyte part, and the non-electrolyte part are separated. This is a basic difference between your RO mechanism and ED mechanism, which is under the application of electrical field. Then we have gas separation technique is there. So the concept of separating gases using membrane is more than 100 years old, but the widespread use of gas separation membrane has occurred only in a few decades. Membrane separate gases only if some components pass through the membrane more rapidly as compared to others. A typical membrane process for a gas separation operates with hydrostatic and partial pressure difference. So here, by use of membrane, there is separation of gases from a mixture is seen, and this include by the application of some your hydrostatic or partial pressure applications is there, and this also depends on the permeation across the membrane. This is very important. Then we have Example, important application of gas separation using membrane are in the production of high purity nitrogen for from air. This is very important. So from air, by the use of gas separation technique, we can separate high purity nitrogen gas, which is mostly used in various sophisticated um, instruments used for different characterization or analysis process. And oxygen enriched from air, recovery of helium from natural gases. So this separation is involved. That is separation of gases, different gases from gaseous mixture. Then we have pore vaporation. Pore vaporation is a membrane separation technique where a membrane separates liquid, feed, and vapor permeates phases. So just see this. So this is the mixture A plus B, and here only the by using a pore vaporation membrane, only the vapor part will separate. That is a vacuum. So some of the component in the liquid fed phase vaporizes and permeate through the membrane, and separation involve phase change. So here from liquid to vapor phase, the phase change will be there. So after the change in phases or phase change, the vapors get permeated through this membrane and it will get separated. So just remember that for vaporization process, the one chamber is for liquid feed, and the second chamber is for your separation, that is separation of the vapor components of a mixture. Then we liquid membrane processes. The process as well as mechanism involved in separation using liquid membrane are briefly outlined as it is by now familiar. A membrane is simply a barrier between two phases. If one component of the mixture moves through the membrane faster than the other, separation is accomplished. A membrane is basically defined as its separating performance and not necessary it should be a solid. Liquid that are immiscible with source, this is very important. Liquid that are immiscible with the source and receiving end can also be used as membrane. The different solutes will have different solubilities and diffusion coefficient in a liquid. So on different factors, this liquid membrane separation process carry out, and we will have the condition is the sample must have immiscible liquids like water and oil. These liquids are not miscible, immiscible. So how to separate these liquids? We can use liquid membrane process technique. The product of diffusibility and solubility is known as permeability coefficient. So just read out these things. What are the different factors are there? So by using the bulk liquid membrane, here it is written, it is bulk liquid membrane BLM, we can separate this immiscible liquid from one another, and this configuration is known as immobilized or supported liquid membrane, ILM or SLM. And the third configuration, which process possesses the largest interfacial area, the receiving phase is emulsified in an immersible liquid membrane. The emulsion liquid membrane, ELM, is there, is also known as liquid surfactant membrane. So under liquid separation process, we have different type of membranes on the basis of the type of liquid we want to separate. And just remember, for liquid separation technique, the sample must be an immiscible liquid mixture, and this partitioning coefficient, sorry, permeability coefficient, this factor define that which liquid will penetrate and which liquid will be at the other end. Then we have transport in supported liquid membrane. What are the type of transport? There is co-transport and coupled transport. So we have example, some chemical reactions in coupled transport. It is let us the metal ion Mn plus reacts with NX minus, and the C is the membrane, that is the liquid membrane. There will be a attachment or adsorption of these ions to the membrane, it will form CMXN membrane. Then CMXN membrane will undergo separation to give or to have the membrane separated, and we have the separation of both the components Mn plus and Nx minus. The liberated carrier molecule diffuses back to the feed solution, and the SLM interface peaks of another metal ion and counter ion, and process continues until the final equilibrium is reached. So this process will continue till the final metal ion or the Mn plus ion gets separated. Then we have the membrane like HC membrane, that is, it may be a organic membrane. So this organic membrane will separate the H plus ion, and will have a if interactive membrane, that is MCN membrane, and again this reaction will reacted with the H plus ion that is liberated, and again we have the metal ion gets separated. And then we have the equilibrium constant, that is product of the concentration of the products divided by concentration of the reactants. We just go through these, and we have another mechanism, that is this is the feed phase, or this is the mixture, and this is the barrier or the membrane, and this membrane will have the phenomenon of adsorption. It will be CMX, and after that, when CMX is again passed through another barrier, sorry, this is the membrane phase. So when this, after this membrane phase, the C will remain, and the M plus X minus will be filtered or separated. So this is a co-transport, and this is the counter transport. So in counter transport, what happen? This membrane, that is CH, will react with M as well as with H. So MC and HC. Then we have the MC will be separated the M plus ion, and the it will also give your H plus. So this middle phase is the separation mechanism, that is the membrane phase. This is, and this is counter transport. Then what are the mechanism? That is sieving is there. That is nothing but your filtration mechanism, that depends on the different size of the pores, and depending upon the pore size, different type of filtration techniques are there: nano filtration, ultra filtration, or micro filtration. Solution diffusion method is there. So where by use of some membrane, the diffusion mechanism is applied, and this mechanism is applied when the membrane is non-porous. From a feed mixture where no appreciable size difference exists for any chemical species to permeate from one side to another, it has to dissolve or adsorb in the membrane and subsequent diffuse through the membrane to get a dissolve on the other side. So there must be adsorption, and then desorption will be there. So this is your solution diffusion. This mechanism is applied when the membrane is non-porous. Then we have preferential sorption or capillary flow is there. So preferential sorption or capillary flow sorption means this include both adsorption and desorption. So the mechanism which involve both adsorption and desorption, this is said to be sorption. So when sorption mechanism is applied to a capillary flow, that means very thin capillary tube is there, then the fundamental approach for the practical development of reverse osmosis process for converting seawater into potable water. So if the surface of the membrane is in contact with the solution is of such a chemical nature that it has preferential sorption for water or preferential repulsion for solute, then a multimolecular layer means it is adsorption. That foreign particles gets adsorbed on the surface of the adsorbent. Preferentially sorbed pure water could exist at the membrane surface. Continuous removal of this interfacial water can then be effected by letting it flow under the pressure through membrane capillaries. So this is based on your both adsorption as well as desorption mechanism by using capillary flow. So this mechanism is effectively applied for converting salty water to potable water. Then Donan effect, ion selective membrane. So we have uh, already read out that ion exchange chromatography. So this is ion selective membrane. So this ion selective membrane means it will include positive and both negative ion exchangers. So it may be cation exchanger or your anion exchanger, and this cation exchanger anion exchangers are used for demineralization of water. This is a industrial phenomena where demineralized water are generally used for various industrial activities. So in that sector, generally ion selective membranes are very big. Ion selective membranes or cation exchange and anion exchangers are used for demineralize the water for their different purposes. So both cation and anion behaviors are there. The chemical structure of ion exchange membrane consists of a network of carbon atoms of styrene nuclei with a suitable functional group attached to styrene nuclei. Styrene means yesterday we have learnt that styrene is nothing but your benzene ring attached with CH double bond CH2. That means one vinyl group is attached to benzene ring and it is named as styrene. If the membrane is immersed in an aqueous medium, it absorbs water and swell due to affinity between the functional group and water. So when these exchangers are used for the separation or the purification, then absorption water is there, and when water gets absorbed, it will swell up, and there will be affinity towards some functional groups and also for the water. Just read out. These are very simple things that how pure or demineralized water is collected by using different selective membranes. That is ion selective membranes. It may be cation selective membrane or anion selective membrane. So these then we will have Nordsen flow. So Nordsen flow or diffusion is one of the possible mechanisms cited to explain the gas separation through membrane. This is gas separation through membrane is known as Nordsen flow. When the mean free path of the gas molecule is small compared to the pore size of the membrane, the formation of the gas molecule is governed by viscous flow or hydrodynamic flow. The flow rate of the gas molecule in viscous flow is directly proportional to pressure gradient causing the flow. Under such condition, the collision frequency between the gas molecule exceeds greatly as compared to collision frequency of the gas molecule with pore wall of the membrane. So this is a physical process where there is pressure gradient is there, viscous flow is there, collision frequency is there. So under this mechanism, your gas separation occurs through different by using different membranes. The situation is known as rarefied gas, rarefied gas, and flow under the condition of usually referred to as free molecular diffusion or Nordsen flow. In Nordsen flow, the component gases flow through the membrane pores independently of each other. That means the gases are separated one by one. The separation takes place due to the difference in their molecular weight. The factor is the molecular weight of the gas to be separated. The principle involved in separation of uranium-235 isotope by means of gaseous diffusion processes. So this Nordsen flow is nothing but the separation of the gas by using different gas membranes or different membranes and by this mechanism the gases are separated independently with respect to their molecular weights. And example is uranium 235 isotope separation by means of gaseous diffusion process. Then surface flow means it is again the formation rate is there, that is surface flow. So surface flow or formation rate of gaseous molecule through the membrane may be enhanced in some cases by surface diffusion mechanism. So in surface diffusion or surface flow, gas molecule adsorb to the surface of the pore of the membrane and then diffuse along the pore walls. So one side it is adsorbed and then other side of the membrane it gets dissolved. So at the interval phase it will be diffused. That one end of the membrane it is adsorbed, at the interval phase it is diffused, and at the other side it will be dissolved. So this under this mechanism your formation rate will be depend on the thickness of the membrane. If the thickness of the membrane is more, then there will be uh, time taken for the process of diffusion will be there, and the separation will becomes slower. Then your facilitated diffusional transport. When a sample diffuse process is coupled with chemical reaction, so this is diffusion with chemical reaction, the net permeation rate may be greatly affected. Such a diffusional permeation is called facilitated diffusional transport. This is facilitated. That means it is the rate is enhanced. How it is enhanced? With the help of or with the assistance of a chemical reaction followed. When there is a chemical reaction occur, then this diffusion process, that is the interval process where diffusion occur, this diffusion process becomes facilitated. So facilitated diffusion occur in liquid membrane system. The mechanism requires a carrier substance X. This will this will react chemically with our substance A, and it will form a compound that is AX, and again that AX will dissociate to give A plus X, and it will get separated. That means by using a chemical reaction this diffusional rate is enhanced, which is known as or which is facilitated. Then active transport is there. All the mechanism discussed so far are non-living membrane. Then permeation of the chemical substance takes in direction from higher concentration to lower concentration. Also, by using a living membrane or a biological membrane, the the separation process is called as active transport or active separation process. Just read this one and try to remember one to two examples. Then these things are there from higher concentration to lower concentration, penetration is there, and under metabolic mechanism, that is under living membrane, we will separate the things. The osmotic phenomena, this is already discussed, that with the help of a semi-permeable membrane, the separation of pure solvent from the solution, that is the flow of solvent from a low concentration to higher concentration is there. So these are some equations, that is thermodynamic equations. This is chemical potential, that is mu I O, that is a standard state mu I O. It is equal to mu I plus delta mu I, which is this is the change in chemical potential. So what is chemical potential? Chemical potential is nothing but your change in free energy with number of moles. So what is free energy? It is also known as Gibbs free energy. This is Gibbs free energy G. So this Gibbs free energy is nothing but the decrease in energy of a system which influence the process to be spontaneous. That to make a process or a phenomena or a reaction to be spontaneous, the energy which is decreased and which is responsible to make the reaction spontaneous, it is known as free energy. So when free energy is changed with respect to number of moles, it is known as chemical potential. And here free energy is equal to STT plus BTP plus summation of mu I plus dni, where dg is change in free energy, S is the entropy, dt is the change in temperature, V is the volume or partial volume we may say, and dp is the change in pressure. And here summation of mu is the chemical potential and capital N is the number of moles of the component. So, by chemical thermodynamics, the equations is there, that is chemical potential equal to change in free energy with change in number of moles at constant temperature, pressure, and rest of the moles. Then what is V? V is equal to, that is volume equal to change in free energy with change in pressure. Then we have the equation like this, that is if I differentiating equation 11.13, that means this one, if I differentiating these two, then we have the equation like this, and finally we have these things are there. Then at the end we have the equation, that is pi equal to CRT, where pi is known as, the osmotic pressure, the C is known as the concentration of the solution, R is the universal rate constant, and T is the absolute temperature or temperature in Kelvin. And this is known as the Van 't Hoff equation, that is pi equal to CR. And and then we have another equation pi equal to ICRT. Some correction terms are introduced by factor due to difference in the concentration, molar concentration of the either end of the solution and the solvent side. Then so this becomes pi equal to ICRT. In reverse osmosis process already discussed, this include your flow of salt solution, that by using RO we can have pure water or purified water or potable water from the salt water. Then we have the equations like this. There is water flux is there, which is equal to QP by A into T, where Q is quantity of permeating solvent. Then having area A and quantity Q, these things are there. Just go through these basic equations are here. Just try to remember these equations. These are depending on your different type of mechanism, and mostly your related to your osmosis. Then we have concentration polarization is also there. The concentration polarization results from the build-up of highly concentrated solute on the membrane surface as compared to bulk fluid solution away from the membrane surface. So this is high concentrated solute on membrane surface. This is known as concentration polarization, where the concentration of the solute is more in membrane, there will be polarization will be there. It will increase the osmotic pressure at the membrane surface, and which causes reduction in water flux and increase the salt diffusion across the membrane. The concentration is the concentration of sparingly soluble salt in the boundary layer adjacent to the membrane surface exceed the solubility limit, precipitation and scaling. So in this part, what happened? Due to polarization of the solute, the water flux will reduce and the salt will diffuse across the membrane. The diffusion of the salt across the membrane will increase. So this is known as the concentration polarization, where the concentration of the solute is on the membrane surface. In dialysis, it is already covered up. Then we have some equations of dialysis. Just go through these things. Then electrolysis also covered up. That at anode and cathode, the anions and cations are moved. So like your cation is positively charged and anode is negatively charged. So negative charge end, the positive ions will remove, will migrate, and for your cation or cathode that is positive, the negative ions will migrate. So there are some equations are there. Here Coulomb efficiency of your electrodialysis process, that is eta equal to number of equivalent of electrolytes displaced from uh, di- dialysate to the brine divided by number of Faraday electricity parts in the process. These chemical equations, so these mathematical equations are there. Then we have Fick's first law. This is Z equal to minus d dc by dx. Then we have ion selective membrane, where ions get selected by the membrane through difference in their uh, polarity. Then we have a limiting current density Im is there. Then halfway potential is there. There is a equation that is Im, that is limiting current density, is equal C dz by delta T bar minus T, denotes the concentration in the bulk dialysate solution, diffusibility in solution, and electronic charge Z, and delta is the thickness of the boundary layer. Then some application, that is desalination of water treatment number one. Then protein recovery. Then we have production of table salt, that is production of salt from seawater. It is nothing but a desalination of salty water. Then hemodialysis, this is application of dialysis in your medical, that is for your kidney diseases, that is replacement of impure blood with pure blood. Ion selective membrane electrode. So these are some membrane of your ion electrodes with some major interfaces. Then we have the equations like E equal to 2.03 active by NF log C by CH. This is your Nernst equation. If a Nernst equation is there, here it is written, Nernst equation is there. In your electrochemistry part, you can have this equation. Then some statistical data are here. Then specific gas probes, uh, detection and analysis of particulate contaminants, and microbiological analysis. So these are some applications of your membrane separation. Just in this part, you just remember that what type of membrane and what is your solution and what mechanism is employed or imposed for the separation. And try to have the some notes. Prepare your you should prepare yourself, and these mathematical derivations may require in your examination point of view. So try to remember or practice these equations. And so now this unit is completed. Then we have the second part, that is we have the second part, that is your unit 12, that is your electrophoresis. And I have one electrophoresis PowerPoint presentation is there. So let's have a 5 minute break, then we will again meet. So thank you. Thank you, students. Let's start our last unit of your paper MCH-002 in your block 5, that is electrophoresis. Yes, electrophoresis. Then we have, am I audible? Anuj, am I audible?
Yes, sir.
Okay. So in electrophoresis part, we have some objectives: electroosmotic flow, basic principle and operation, different forms of electrophoresis, slab electrophoresis, DNA gel electrophoresis. This is SDS page gel electrophoresis, two-dimensional SDS, then capillary, capillary zone, capillary gel, capillary iso isotachophoresis. Then we have we have isoelectric and capillary electrochromatography. So these are in very briefly this will discuss. Then I just have this one, and it has 96 slides. So I will move little fast. So he is regarded as the father of electrophoresis. This is Arne Tiselius. So these are my contents. So introduction is: electrolysis is a migration of charged particle or molecule in a medium under the influence of an applied electric field. So this is as we studied in class 9, 10, 11, 12 in electrochemistry or electrophysics. We have a general principle on electrolysis which is proposed by Michael Faraday. So this is just migration of migration of charged particles towards their respective electrodes under the influence of a definite medium, and also influence of an applied electric field. So this is cathode and anode. So cation is positively charged, so that's why cathode is a negative part. Anion is negatively charged, so anode is positive. So this is your electrophoresis setup. Then we have the migration of an ion depends on net charge of the molecule, that even the charge is higher charge will migrate faster. Size and shape of the particle, so small size will migrate faster than the large size particles. Strength of the electric field, when electric field strength is more, then migration will be more. Properties of the supporting medium, so this is the supporting medium, this is the electrolyte used. So the electrolyte used, how the electrolyte concentration or the type of electrolyte depends or affects the migration of different ions. Then temperature effect is there, the ionic strength of the buffer, that is the pH effect we will discuss. So this is what should we expect if a macromolecule has a net charge q and an electric field. So when, so this is nothing but your Coulomb's equation, that is F equal to Q into E, that is electrical force, and finally we have V equal to QE by F, where F equal to 6 pi eta A, that will be their respective meanings. And here two types of forces are applied, that is electrical force and frictional force. So frictional force is V into F and electrical force equal to QE. So V becomes QE by F. Then we have your, we have the electrophoretic mobility, that is mu, electrophoretic mobility, that is V by E, and which is equal to charge by field strength F. So electrophoretic mobility is defined as the rate of migration in terms of centimeter per second per unit field strength, that is volt per centimeter. So mu equal to q by 6 6 pi Rn, and with their respective meaning. So these are mu electrophotic mobility, q is your net charge, r is the ionic radius, n is the net viscosity. So this is effect of heat, so how thermal effect or heat effect is there for the migration of different ions from their respective ends. This effect of heat will be the peak will broaden. So flat peak will be there, and the resolution will be decreased. Then formation of your just wait. Then formation of your temperature gradient, that is change in temperature with area, then convection current resulting mixing of analytes, then denaturation of enzyme and proteins. So these things can be seen or by the effect of heat on electrophoresis. So as Ohm's law stated that V equal to IR, so when heat increases the resistance will decrease, and V equal to IR. So when the voltage become constant, then current increases and resistance decreases, the migration will increase, because with increase in current, the migration of the ions will be faster. This is nothing but your Ohm's law. Then electroendosmosis, the movement of liquid out of or through a porous material or a biological membrane under the influence of an electric field, each called electroendosmosis or electroosmosis also it may be said. That is, this is the movement of the liquid particle through a porous material or biological membrane under the influence of electric field. It is known electroendosmosis. This is surface of gel is negatively charged. This is a pictorial view of your endosmosis. This is surface is a gel that is negatively charged. Surface gel ions are immovable. This is not immobile state. This is static state. The buffer is 8.6 here. Orient with the negative surface and equal to positive ionic cloud. If there is positive ionic clouds are there, so this will move at their respective part. Ionic cloud is mobile, so electrical current causes positive ion cloud to move towards the cathode. The positive ion will move towards the cathode, and this is the supporting medium, and this is the gel, which is very much stationary in your electroendosmosis. So macromolecules are generally that have a sufficiently strong enough charge are able to oppose the flow of positive ion cloud and move into the opposite direction towards the electrode of opposite polarity. So this electrophoresis is nothing but migration of ions, and on the basis of their on the basis of different factors which influence the medium, which influence the field, which influence the electrolyte or the formation of the ions or the migration. These factors are responsible for the effect of electrophoresis for their separation of the component in a mixture. So again, in electron endosmosis, molecules on surface. This is molecules and macromolecules with weak negative charges. This is the application point, and this is a positive ion electrode cloud. So this surface of the gel that hold a weak negative charge, because this is already negative, so and this is also negative. So this is will negative charge pushed towards the cathode. So this will push towards the cathode. It will push these negatively charged molecules towards the cathode, despite migration direction towards the anode. So this is endosmosis, and these are the fixed layer, diffuse layer of just keep this one. This is the migration part, that is positive will migrate towards cathode and negative will migrate towards anode, and there will be weak flow. A term is there, that is weak flow, that is movement of buffer into support medium. During electrophoresis, heat evolved because of passage of current through resistive medium can cause evaporation of solvent from electrophoretic support. This drying effect draws buffer into support, and if significant, the flow of buffer can affect protein migration. So this is effect of buffer and movement of buffer in the supporting medium. That is, if the medium is gel medium or liquid medium or anything else, then the electrolyte or the buffer or the medium which we have used for the separation, there will be a drying effect which draws buffer into support, and this is known as your weak flow. This is your conventional electrophoresis. So this is the actual instrument, and this is the computerized one. And here what happened, there is a bed which is nothing but your gel slab is there, and this is sample well. Samples are injected on this well, in this well, and there is then this is connected to their respective parts, and this is positive part and negative part. So by applying these samples here, the different ions will migrate in there to their respective electrodes, and the electrolytic solution is here and here. This is the electrolytic solution which are directly connected to their directly connected to the two ends of the supplied electricity. So the buffer used to control the pH. The for the different purposes for the use of buffer is carry applied electrical current. The pH is set up, and the buffer is also determine type of charge on solute, extent of ionization, electrode towards which the solute will migrate. The buffer ionic strength will determine the thickness of the ionic cloud. So these are the factors and effects buffer will impact to the electrophoresis mechanism. Then, for example, if we have the pH analysis, then every amino acid has its own specific isoelectric point. That means at the one electric point, the every amino acid has its own specific isoelectric point. That means iso means same. That means same your voltage or current or electrical parameters. Since proteins are made up of amino acids, all protein have their own pH. That is a pre-albumin, it is 4.7, 4.9, 7.3. So this is your isoelectric point, that is pi. How charged a molecule become depend on pH of buffer, and protein of isoelectric point is there. Then this is one pictorial view of your pH, effect of pH on different ions during their migration. This is a pH paper or your litmus paper, where the either end, this is the acidic part and this is the basic part or alkaline part, and the middle one is your neutral part. And this is some examples of your buffer to be used for different electrophoresis application. Then supporting medium, this is the we can say this is the bed on which we placed our sample for separation. The supporting medium is a matrix in which the protein separation take place. Various types has been used for separation either on slab or capillary form. Separation is based on charge and mass of the protein depending upon the pore size of the medium. So this depends on the pore size, and also this will treated as a matrix or a bed on which the sample is placed. So there is some parameters: chemical nature, it should be inert; availability, easily available; conductivity should be high; adsorptivity should be low; sieving effect should be desirable; porosity should be controlled; transparency should be high; and electroendosmosis should be low. Then preservation is feasible, toxicity is low, and preparation should be high. So these are some basic things needed for your supporting medium. So various supporting materials are starch, gel, cellulose acetate, agarose, polyacryl, amide gel. So amide gel is these materials are generally used for your supporting material. That is the to prepare the matrix or the bed for electrophoresis phenomena. Then we have zone electrophoresis, moving boundary electrophoresis. Then under zone we have paper, gel, cellulose acetate, isoelectric and immunoelectrophoresis. Under moving boundary we have capillary and isotachophoresis. Then this is the paper one by using a paper that is a filter paper. It will be Wattman 1, Wattman 41 type, and we have two different plates are here which are connected to two different ends of the electric supply, and we have separation time of 12 to 14 hours for separation of migration of ions, and generally Wattman number 1 filter paper is used, that is of 3 millimeter in strip and 3 to 5 centimeter wide. This is economical and very easy to use, but disadvantage is only protein hydrophilic molecule cannot be resolved properly due to the adsorptive and hello କୁହନ୍ତୁ କୋଉ କାମ କହିଲେ ମୁଁ କଥା ହେବି ଆଉ ମତେ ସମୟ ଦିଅନ୍ତୁ ଆଉ 20-25 ମିନିଟ ନାଇଁ ନାଇଁ ସରିନି ନାଇଁ ସେ କାମ କରୁନି ଅଲଗା କାମରେ ଅଛି ଗୋଟେ କ୍ଲାସ୍ ନଉଛି ଗୋଟେ କ୍ଲାସ୍ ନଉଛି କରି କରୁଛି ହେଲା so these are some disadvantages then we have gel electrophoresis where gel is used as the matrix and where the separation is brought about through molecular sieving technique based on the molecular size of the substance. Gel material acts as molecular sieve. Gel is a colloid in a solid form that is 99% water it contain. It is important that the support media is electrically neutral. Different types of gel that are used is agarose gel, starch, polyacrylamide. So depending upon the type of gel used, different type of materials or mixtures get separated through this electrophoresis phenomena. And one important thing is there in gel electrophoresis, the gel which is to be used as the matrix should be electrically neutral, and it should have a definite molecular size. Then this is the agarose gel where a polysaccharide is the repeating unit having concentration 1% to 3%. Pore size is controlled by the percentage of agarose used. Then we have advantages and disadvantages. Easy to prepare and small concentration of agar is required. Resolution is less. Resolution is superior to that of the filter paper. Differential source and batches of agar tends to give different results and purification. If is often necessary, I will share this PPT. Don't worry. Yeah? Then we have so this is the mechanism of a gel electrophoresis. So this is the matrix. Okay, sorry, this is the casting tray. That is the bottom one, the casting tray. So so above this we put the agarose solution. This is the agarose solution which we have poured, or then by using a comb like thing, we will symmetrialize the bed, that is the agarose bed. Then we will put the sample here, and just remember this agarose gel is electrically neutral, and I put sample here. This sample will penetrate into this gel, and this will get separated when it is connected to the electrical supply. There is only migration of ions. These things are there. Then troubleshooting, these things are not required. Just keep these things. Already discussed. Yes, the second one is polyacrylamide gel. Here, polyacryl amide gel is used as the matrix. This is cross-linked. An example is in India's methylene bisacrylamide, and the percent is this one, and pore size. This is the reaction that is, and here the free radical mechanism is operated by the acrylamide monomer. Then SDS page is there, which is nothing but a sodium dodecyl sulfate SDS and a polyacryl amide gel electrophoresis. So this is polyacrylamide gel electrophoresis, that is PAGE page. SDS is sodium dodecyl sulfate. So this is used as your matrix. The most widely used method for analyzing protein mixture is useful for monitoring protein purification, as separation of protein is based on size of particle, can also be used for determining the relative molecular mass of the protein. So just remember the full form of this, and this method is mostly used for the purification of the protein depending on the different size of the particles. And also we can have the determination of molecular weight of the protein with this by using this technique, that is SDS page PAGE. So SDS is nothing but your sodium dodecyl sulfate polyacryl amide gel electrophoresis. So this is SDS is an anionic detergent. The sample is first boiled for 5 minutes in buffer containing beta mercaptoethanol and SDS. So first the sample is boiled for 5 minutes, and this SDS is an anion detergent like soap or detergent type. So this is the this type of protein, that is native protein. When boiled for 5 minutes, it gets a straight chain and is denatured now. So each protein is fully denatured and open into rod shape with series of negatively charged SDS molecule on polypeptide chain. So on each polypeptide chain, there is series of SDS molecular gets attached, and the important thing is the protein becomes denatured. That it denatured and opened into a rod shaped structure. Then on average, one SDS molecule bind for every 2 amino acid residue. Hence, original native charge is completely swamped by negative charge of SDS. Then we have the components of your SDS page is just like this. Then this is the pictorial form. This is the actual one, SDS page. Yes, this is the one, and we have some power supply here. Anode is here. This is the anodic part, and this is the cathodic part is there at the top, and we have the separating gel matrix is here, and we put our sample in this sampling chambers, and by different particle size this will get separated accordingly. And we have some buffer is used. So this is on the SDS page, that is your electrophoresis mechanism. Then the gel used in SDS page is stacking gel, running gel. Stacking gel is ordering, arranging, and concentration of macromolecule before entering the field of separation. Purpose is to concentration protein sample in sharp band before it enters the main separating gel. This is your stacking gel. There is orderly arranging and concentration of macromolecule. This is before the entering of the field of separation. And here 4% acrylamide is used. Acrylamide is used. And here 15% is used for zone separation. So this is your one view of your separation, that is a stacking gel, and this is a resolving gel. This is 4%, and this is your 15%. Then movement of the particle by the process of HDS page, that is chlorine and it is glycinate, gets separated under different pH condition. And this is mixture of macromolecule, that is the protein one, and the different particle with different charges, that is positive and negative charges. Under this influence of this HDS page, this will separated on the basis of their interaction or migration. Then this is some uh, diagrams or mechanism of your HDS page, that is sample is this is sampling is done here. This is your anodic part, this is your cathodic part is there, and this is gets separated by the mechanism of your electrophoresis. I just what are the applications? This used in research tool, measuring molecular weight, peptide mapping, protein identification, determination of sample purity, separation of protein and establishing size, blotting also it is used. Then smaller fragments of DNA can be analyzed by using this method. What are the advantages? These gels are stable over wide range of pH and temperature. Gels of different pore size can be formed. Simple and separation speed is good comparatively. Exhibit reasonable mechanical strength, low endosmosis effect. Okay, these are some advantages. And what are the disadvantages? This is time consuming, carcinogenic also. This is complete reproducibility of gel preparation not possible. Then the staining part is there, fluorescent stain. The staining is not needed in your, they're not there in your syllabus. So I skip this one. Native buffer gel done by using polyacrylamide. So just remember this compound, polyacrylamide gel, and this is mostly used in your electrophoresis technique. 7.5% if in your native buffer gel, and their sodium diosylate sulfate it is absent, HDS. pH is 8.7. Proteins are separated according to electrophoretic mobility and sieving effect. Isoelectric focusing, it was first discovered by H. Venson in Sweden. Method is ideal for the separation of amphoteric substances. Then this is under different gradient of the pH. The separation is there. So the pH, when the pH increases, the separation becomes accordingly. Establishing of pH gradient. This is actually not there in your syllabus, I think. Then we have capillary electrophoresis. So let's see where is the capillary one. Two-dimensional. This is your capillary one. Yes, this is isotachophoresis. It is there in your syllabus. That is, it is used for separation of smaller ionic substances. They migrate adjacent in contact with one another but not overlapping. This is an unique mechanism is there. They are migrate adjacent to each other, but they do not overlapping. The sample is not mixed with buffer prior to run. Hence, current is flowed. With the current flow is carried entirely by the sample ions. Faster moving ions migrate first, and the adjacent ones next, with no gap between the zones. So this is known as isotachophoresis. In isotachophoresis, the smaller ionic substances get separated and they migrate adjacent to each other. No overlapping is observed, and and also they carry the electricity pass through it or the current flow through them. All ions migrate at the rate of fastest ion in zones. Then it is measured by UV absorbance. Application is separation of small anion and cation, amino acid, peptide, nucleotides, nucleoside, and protein. Pulsed field electrophoresis. Power is applied alternatively to different pair electrodes. The electrophoretic field is cycled cycled at 105 to 180 degree, because of which the molecule have to orient to the new field direction. This permits separation of large molecule like DNA applied for typing various strain of DNA. This is pulse field. So different pulse electricities are applied. So just see here, there are two cathodes and two anodes are here at 120 degree angle. The electric field alternates 120 degree every 90 seconds for 18 to 20 hours at 14 degree centigrade. So this is just a different setup for your pulse electrophoresis. Then immunoelectrophoresis is there. It refers to precipitation in agar under an electric field. It is a process of combination of immunodiffusion and electrophoresis. An antigen mixture is first separated into its component parts by electrophoresis and then tested by double immunodiffusion. So this electrophoresis technique is mainly used for your biological samples, and where things like antigen are placed into wells cut in gel without antibody and electrophorused. A trough is then cut in the gel into the antibodies. These are not needed. Immunoelectrophoresis is not there in your syllabus, I think. No. Just keep this one. This is a biological method. Anyway, capillary. This is in our syllabus. So this capillary electrophoresis was first introduced by Jorgensen and Lucas in 1980. As the name suggests, a narrow bore capillary is used for the separation. A very narrow bore capillary is used like this. This is the narrow bore capillary. The components are the reservoir, that is the electrolyte or the buffer part. The electrical buffer is there. Then power supply. It is the high voltage supply is here. This is the capillary tube. Detector and computer here. This is the detector and this is the computer. And sample, and one thing is there, that is sample applicator, where sample is injected. So this is the component of your capillary electrophoresis part. Sample application is done by either of one method, high voltage injection or pressure injection. So if it is high voltage injection, the buffer reservoir is replaced by the sample reservoir. The high voltage is applied. Just here, it is the buffer reservoir here. Here, when sample injected, this buffer reservoir is replaced by sample reservoir. So this becomes the sample container. So when the sample is introduced, the buffer reservoir is replaced by your sample reservoir. The high voltage is applied, buffer reservoir is replaced. Okay, the voltage is applied for the separation. For a pressure injection, anodic end of the capillary is removed from buffer and placed in air-tight sample solution with pressure sample is pushed into the capillary. Then pressure mechanism is used, when pressure mechanism is used, this anodic end is removed. Okay, this anodic end is removed and airtight sample sole is connected here, and this will pump up the sample into the chamber. With pressure sample is pushed into the capillary, kept back in the buffer sample, and voltage is applied. High voltage is applied, the component migrate at different rates. Although separated by the electrophoretic migration, all the sample is drawn towards cathode by electroendosmosis. Since this flow is strong, the rate of electroendosmosis flow is greater than the electrophoretic velocity. Positively charged molecule reach the cathode first, that is electrophoretic migration plus electroosmotic flow. So the positive ions will reach first at the cathode end. This is the detection or peaks of your capillary electrophoresis. Just keep these things. Clinical application. This is multiple myeloma testing. This is globinopathy screening. This is again medical term. This is SPA1C, monitoring chronic alcoholism, or in short is GGT. Advantages over clinical one: online detection, improved quantification, almost complete automation, reduced analysis time. Microchip electrophoresis. This is again another advanced version. The current advanced method development in technique include integrated microchip design, advanced detection system, new application, protein and DNA separation can be done. And this is the microchip model setup. This is separation chamber is there. This is the separation chamber. Sample injection is here. A reservoir is here. Voltage is supplied. Then sample preparation, pre-column and post-column. Classical cross T design. This is classical cross T design. Time period of 50 to 200 seconds. It will take. Then these are the detectors: laser induced fluorescent detector, electrochemical detector, pulsed amperometric detector, and sinusoidal voltammetry. So these are some detectors used in your microchip electrophoresis. And there are some references are there. And if I go to this, I almost cover all the things in this unit. And uh, to cover these things in detail and in bit by bit or line by line mode, it is very hard to cover all the things within 1 hour, because we have very limited period to complete the total paper within 7 days, which is not possible. This one block will take 7 days. So you have 5 blocks. So that's why I prepared or I have collected some PPTs from different sources, which are very much helpful to us to cover these units. And today I will share all the PPTs to your WhatsApp group, and hopefully these PPTs will help you to understand the things and to memorize the things for your examination point of view. And tomorrow we will discuss the high performance liquid chromatography section first, because we left at the middle on that day. And the second part, that is the rest half an hour or 1 hour, we will discuss different things, your queries or anything you wish to say or share. And just in membrane separation as well as in electrophoresis. In the first part, you should remember the type of membrane, the different pore size, and if you understand these two things, then the um, then the process or the mechanism will automatically come. Then what is the membrane type, what is the pore size, and what is the mechanism. Then the process or the name of that membrane separation will automatically come, and you will write easily. Followed by your electrophoresis technique, it is again the same thing, that which type of matrix you are using for the sampling process, or what is the bed you are using for to place your sample. So this defines your type of electrophoresis to be used for the separation of different component in a mixture. And you have many theoretical things, many questions are there. Just I try to touch you all the parts of these different units of your different blocks, and the important things I already highlighted. And just give into importance to this part. And tomorrow we will be the last day, and on that day we will discuss all the units. If you have any doubt and related to your theoretical exam, I will suggest you some things. And uh, do not worry for your practical examination or practical classes. It will be conducted um, after the end of your theory classes by 28th February, I think. It is the last day of your theory class. So after that, your practical class will held up and will be held, and then after your practical examination will be conducted. So thank you to all, and yeah, your queries and your the remaining discussion we will have tomorrow. So till tomorrow. So thank you to all for your patience hearing, and we will meet again. Thank you.